All right. I think it is recording now. So yeah, welcome. And this is After Hours for CSEU4 data structures. I'm going to start with queues and stacks. And there's also in the thread After Hours here, there's a GitHub link where we'll be sharing the code. And yeah, if there's any questions, just let me know. All right. So getting started with queues. Does anyone here want to explain their version of how a queue works? I guess not. All right. Yeah. So a queue is first in, first out kind of data structure. So the most recent thing you put in is the one that's going to come out. Okay. So I have an example here using linked lists with a bit of an animation. So if I, let me just clear the queue. Okay, yeah. So let's see, I add 6, right? It creates a linked list here and we have it here, right? I have head and tail. Let me just reduce this. This is, all right, it's a bit better. Right, so that's a node, right? We have head connected to the tail, connected to this node, and then this node connected to the tail. So if you enqueue more, this will happen, right? Where this node will connect to the new node, and the new node will become the tail, all right? So every time you add a new one, that will happen. So the last node will connect to the new one, and the new one will become the tail. Is that any question about this? So I'm sure you've all seen a queue implementation so far. So I'm going to move on to stacks. So stacks is just kind of an opposite to the queue, where you have last in, first out kind of structure. This means that, let's see, I have it right here so I don't switch them up. We remove the most recently added element. All right, so let me change the link here and refresh. So yeah, with the stack, it's a bit different. So if I push the same numbers, 7, 8, 9, 10, we're gonna have the same thing. So we start at the top of the stack, but now as you can see, the order is different, right? Now the 7, it will become the last one instead of the first one, because every time I add a new one, the new one will become the first. Does that make sense? Where in the queue, a new one becomes the last. All right. Any questions so far on how queues and stacks work? So yeah, the difference between queues and stacks is mostly how you remove things. This is why we call them FIFO and LIFO, right? First in, first out for queues, last in, first out for stacks. In a queue, when we remove an item, it's the least recently added. So here, if I dequeue, that will be the 7 because it's the oldest thing in the queue. All right. Well, when I go to the stack and I remove an element, I pop. The 10 got removed because it was the most recent. So yeah, the queue dequeues the oldest things, and the stack pops the most recent things. Yeah. And then, yeah, we have a challenge here where we would implement a queue data structure, but only using stacks. Does anyone want to comment on this challenge? Does anyone have an idea on how to do this? You guys can talk. I think you have the mics. All right. Well, if not, I'm just gonna start going through it, right? So we would start a class queue, right? Define the init method, just a normal start to this queue, except here we can only have stacks. So in this case, I'm going to use stack 1 and stack 2. Then let's see, we need to have the enqueue method. So this will have self and the new item here coming in. Pseudocode for this would be we first need to move all elements in stack 1 to stack 2. So yeah, so we move all the elements first from one stack to the other. Then we push the new item into the stack 1, and then we move all elements. Well, let's call it items because be consistent. In stack 2 to stack 1. So yeah, just a bit of back and forth where we have the stack 1, which will make sure that the oldest element is always at the top of stack 1. Okay, so this means that our stack 1 is kind of the main we're going to use, and the stack 2 will be like a backup storage for us. So we can do this using a while loop. So if I do length of self.stack and do it while it's not 0, so do it until the stack becomes empty. Let's move all the elements. So take the last most recent, let's see, yeah, most recently added item in stack 1 and add it to stack 2, and that could be done using self.stack2.append the last item, so the one at the top of the stack, that's gonna be like this. And then, yeah, we just remove that last item from stack one. So that's just self stack one. Pushing, it's pretty easy. So we just do self.stack one dot push, and we push the new thing, right? Then it's kind of very similar to this. So I'm just gonna copy this code here. It's just backwards. So now we're checking stack two and moving all the elements back to stack one. Okay. So this will be stack one, this will be stack two, okay. Questions so far? Is anyone understanding this? Comments or otherwise? Is anyone alive here? No one seems to like using stacks so far. All right. DQ is gonna be a bit shorter. So for DQ, we're just gonna check our stack one because that's the main one we're using. So let's see if the length of self.stack one is 0. It means we don't have anything. We don't have anything in this queue, so we can't DQ. I'm just gonna say print queue is empty, return false. All right. Otherwise, let's see, return top of stack one, which is the oldest item. Yeah, and then of course remove it from the stack so it doesn't get lost. So we could do this by saving it in a variable. When I do this -1, it means that it's the end of the stack, so it's the top of the stack. And then, yeah, just remove it. And return it, of course. So this is an implementation of a queue using just stacks. Does anyone have any questions about queues or stacks?
Yeah. So, like, okay, I do understand the concept around the whole queue and stack thing, right? So, but the truth is, visualization is for some reason somewhat tricky. So while you were implementing, I was trying to visualize how it was supposed to work, what the result would look like. But yeah, first of all, like I think on line 27, okay, now let me start from the beginning, right? So we have a class queue, then we initialized the stack one and then the stack two. Then in order to add into the queue, we have to, first of all, check why the length of the first stack is equal to 0. So if that is 0, we append. Okay, so yeah, I think I'm confused. Yeah, I'm confused on that particular block.
So while this stack has any items, so the length is different than 0, means that while this stack has something inside of it, we're gonna move it to stack 2. Okay, so basically, we're gonna make stack 2 save our stack 1, but in reverse. Okay. This means that if stack 1 had 1, 2, 3, 4, stack 2 after this while loop would be 4, 3, 2, 1. Okay.
So that's why we have the -1 on the index means we're starting from the last element
From
on the stack 1.
yeah, from the top. So yeah, from the last element on the stack, which is the top of the stack. Okay. So it's the most recently added thing. Okay. So we go from most recent to oldest, which means, for example, our stack 1 holds items from old to new. Okay. And this one holds items from new to old. Okay. Does that make sense?
Okay, so just to clarify, right? So let's say we have the first stack, and then it's an empty array, right? So and then we push to it. It means we push 1 initially. Then when we push again, it means we're pushing 2 onto it, which means 2 will be in front of the 1, right? So just like that, that's why you're saying it's from old to new, right? So it means the most recent value we'll be pushing to the first stack would be 4, right? Then if we're then pushing the stack 1 to the stack 2 and we're doing it in reverse, it means we're now starting from the newest element, right, which is from the 4 down to from the 4 down to the 1.
I'm sorry, I lost you there. Can you reiterate?
Yeah, so I'm trying to visualize the layout, right, based on this array we have for the stack 1, right? So I'm assuming we have stack 1 is an empty array, right? Rather, it's an empty stack and we're trying to push to it. So we have 4 values we want to push to it. So let's say we push in 1 initially into stack 1, right? So we would have 1 inside, and then the second value we push is 2. So it means we would have 1, 2. Is that correct?
It means that um, our queue will have 2, 1. I think yes. So,
Oh, I'm asking
but
about the stack.
our stack will our stack. Yeah, I think. Let's see. So we in queue 1, right? In Q1, and then it just remains with 1. Then we in Q2, this means that we have 2 and 1. So what happens is after we in Q1, okay, in Q, oh, sorry. After we in Q1, this is stack 1, okay? So in Q1, stack 1. And then when we in Q2, what will happen is all things in stack 1 will move to stack 2. So first, this one will go to stack 2, okay? So this will be empty. And then we're gonna push the number 2. So then we're gonna have 2, okay? And then everything from stack 2 is gonna move back to stack 1, meaning that it's gonna end up like this.
Still a bit confusing.
So let's see if I clear this. Okay. Okay. If I push 1 and 2, right?
Yep.
Let me make this a bit much faster. Okay, 2. This is the stack, right? I pushed 1 and 2. We have
Okay.
2 and 1, right? This is the stack 1, right? If you push 1 and 2, right, by that order, okay? But your queue, right, if you queue 1, let me make this much faster as well. Q2 is different, right? This,
Yeah, I get it.
okay, so this is why our VQ returns from the top of the stack, so the end, right? Because if you look at from the end to the start, you have 2 and 1 on our queue, and it's just like our stack, right? 2 and 1. It's just a matter of reversing the order, because I know it might not be that easy to just reverse in your head, right? Reverse the order, but this is what happens, right? If you enqueue 1 and then 2, this is our stack 1 value, 2 1, right? And that's because we do this moving around. We place our previous elements in stack 2 before we add to the stack 1. Okay.
Okay, yeah, so we wouldn't have to lose it. The first. Okay, yeah, I think I get it right. So where I was basically confused was in terms of if we're pushing, like if we're pushing to a stack, right? Not the queue now, right? So if we're pushing to a stack, on the visualization tool, we have a top, right? So, but since if we're using an array like on the code there, I was trying to visualize how the layout would be if we're trying to push here. So, but I think
Yeah,
you showed it on your line 2021 there.
yeah, don't get distracted by this array. This is just so we don't have to implement a stack class, but it works very similar. Okay, so it works very similar to a stack, the way I did it here, right? It just, you wouldn't have this -1. You probably would have to have another method called peak at the top or something, or just another method that would help you look at the top of the stack. And yeah, append will probably be push on a stack class, right? But it's very, it's almost the same. Okay. uh,
Yeah.
is that, yeah? Any other questions about this? This is also an hacker rank challenge. And yeah, I can give you guys the link. But yeah, it's also something you can take a look and get some points and things on your hacker rank. All right. I think that's everything for queues and stacks. If there's nothing else, I think I'm gonna move on. Who wants to go next, Ifyok or Victor?
I guess I can go since mine is quite straightforward. Okay, give me a second. All right. Just let me know when you can see my screen.
Yeah, we can see it.
All right. Okay, so we'll still be touching on linked lists basically. So the purpose of this short one is for us to solve a linked list problem. But before we solve the problem, I guess even though Melky has touched a bit on linked list before he started talking about the stack and queues, let me just, touch a little on it again. There's no harm in us sounding like a broken radio. So we all know what linked lists are. So I'm not going to start the whole definition thing, but I'll just go straight to it. So we've been told about two types of linked list: the singly linked list and the doubly linked list. And we know that the singly linked list is basically different from the doubly linked list based on this extra ability that the doubly linked list has. So basically, for our singly linked list, say we have one, let me see, I can type fast. We have 2, 3, and let's see, we have 3 here, then we have 4 here. So for a singly linked list, in this case, this 1 is our head because it's the first element in the list. 4 is obviously the tail for obvious reasons as the last element in the list. Okay, then in order to navigate through this list, head.next will be 2. Okay, so head.next will be 3, and then we can use pointers in our linked list to point to the next element in our list, basically. So in singly linked list, we can only point one way, which means we would have, say, let's set head now to be 1, and then let's set head to be, let's take our current element, basically. Current.next will be 2, current.next would be 3, and so on and so forth to the end. But we cannot, go back. We don't know what is behind it. So in this case here now, for our singly linked list, I write singly here. In this case here, hold on. How do we do that? Oh, okay, I have to have it on the other side. So let me have it here. Okay, so in this case here, we can only go forward. Like 2 doesn't know what was its previous, 3 doesn't know what its previous was, and so on and so forth. But when we're dealing with doubly linked lists, this is a different case now. It's more like special, because here now everybody can keep track of who they came after and who is, basically everybody can keep track of who is in front of them and who is behind them. Yeah. So for a doubly linked list, we have the head.next. So now this is our current element, right? So current.previous, we have a previous, we'll note that is 1. So basically for the doubly linked list, we can go back and forth, but for the singly linked list, we can go in just one direction. And things we should know: this is our head, this is our tail, these are our elements here in the singly, and then the nodes basically is what connects this guy to this guy. So let's have that picture, that mental picture at the back of our minds. Okay, so now, having understood the basic concepts behind linked list, now if this explanation doesn't still make a lot of sense to you, I shared some resources on the main channel that broke down linked lists even further. Okay, so if this doesn't make sense, you could always go back to check out those resources. So now, having understood the basic concepts behind singly and doubly linked lists, we're going to take up a problem and try to implement a linked list in it. So now the problem really is pretty straightforward. We're just supposed to remove the duplicate values in our linked list. So write a function that removes the duplicate values in our linked list. So basically, what it means is if you are given this value 1, a linked list contains 1, 2, 3, 1, 4, 2, 5, it should return a new linked list without the duplicates. So basically, what our function is going to do under the hood is this. So we're going to loop through this guy a bit. So let's bring this out here now. So what this is saying is now our first element in this array, in this linked list, sorry, is 1, right? Okay, so now the next one is what? 2, and then the next one, that's current.next now is 3, right? Then now current.next is now 1. We already have 1 in our list, so we're going to eliminate this guy and then point this guy to this guy. So let me repeat that. Because 1 is already in our new list, we're going to get rid of 1 and then point 3 to 4. So instead of the current.next at this point to be 1, it will now be 4. So the next one here now will be our 4. And then now current.next now is 2. We already have 2 in our list. So for us to move ahead and for us to delete this guy, we just point 4 to current.next, which is 5. So there's something I read somewhere, and basically for linked lists, there's no true deletion. We're just changing where the pointer is. So when they say you're deleting, like really you're not, like you can't prove that you're deleting anyway. You're just changing where the pointer goes. So at this point, we have our new list with without duplicates, basically. Okay. So I hope we understand like the technique we're going to use now. So the idea that Storm gave us is use the upper right. So you understand the problem, you plan a solution, and then you execute, and then you perhaps revise, right? So at this point, I'm guessing we've understood what the problem is. So the next thing we're going to do is to perhaps plan what we're going to do, plan an attack, or whatever we'd call it. Okay, so now the first thing we're going to do, let's just talk about it now. So we're going to check, before we start, yeah, since we're going to work with a linked list, I think what I'm going to do is I'll just bring in a linked list that we've done before. So I'll just take the same here. Okay, so let me just dump that there. So we have a linked list now. Okay, with the node. Okay, all right. So let's do this and keep on side before we continue solving. So what's we'll be working with Doubly linked list. Okay. So that means so this is telling us basically that our function is going to be taken in a doubly linked list, right? So now what are we going to do? So the first thing we're going to do, okay, is to check if the linked list is empty. Now, if the linked list is empty, it means there is nothing in it. There is no duplicate. There's nothing. So we just return it as empty, right? So perhaps let's have our pseudocode here now. So let's check if linked list. Hold on. Okay. So check if linked list is empty. So to check if linked list is empty is very easy. You can just check that's basically to check if head is none. So if there's no head, we don't think, like if there's no head, like it's the same thing as saying it's empty basically. So we check if the linked list is empty, and if it is, we'll return none basically. Okay. So now that's like our base case. So in the case where the linked list is not empty, that means we have values inside our linked list, right? So the first thing we're going to do is to set our current. So we're going to sort of set the head to be our current value so that we'll keep track of the current value that we'll be moving with, okay? So the next thing I'm going to do now is, okay. So set the head as current value, okay? So while the head is our current value, we want to keep track of this list, right? We want to keep track of everything we're looping through. So in order to keep track of that, we're going to create what they call it now. We're going to create something. We're going to have a container kind of that is going to hold what we're pushing in, each element we're pushing in. So we'll say, so let's create say a container, okay, that holds each how we put it now, each element from the linked list. So it's not just going to hold each element, it's going to hold each unique element, because the idea is to get rid of the duplicates. So something we can think of that would hold only unique elements from a list is we can use a set and save it in a list. So let's just keep this here. Say this is like a reminder to us now. Use set function basically. Okay. So set is one easy way that you can use to get rid of duplicates inside a function or inside any can use to get rid of duplicates basically when you're working. Okay. So now when we've created a set that will hold our current what do you call it now? Our current item in an array. Now we're going to loop through the linked list itself. So we're going to loop through the linked list and we're going to check while current.next is not none. So if current.next is none, it means that we've reached the end of the array, and at that point in time, like, we're supposed to stop and return. So perhaps let's make note of that. So if current.next is not none, that implies that we're at the end of our linked list. So you can say return the linked list that we have. Okay, that is so that we'll not have to write a return twice. That's going to be the last thing that will go on. So now we'll check. I'm trying not to write code. I'm trying to make it sudo. Okay. So let's see. Looping through the linked lists. We're going to check now. So that's while current.next is not none. We're going to check. We'll check if current.next.value is inside our visited container. That is inside our container. If current.next.value is inside our container, then we'll delete it. And then let me just show you what we want to do at this point. What is that explanation we had? Let me bring it down. So use that to keep track of what we're doing. Okay. Hold on. Let me just drop it here. Okay. So what we want to do now, where are we? Let's see. So let's go through. So if current.next is not none, we are at the end of our linked list. So return the linked list, right? Now, while we're looping through the linked list, what we want to do now is to check. As far as the value that we are on, as far as the current value is not inside, as far as our current value is inside, rather, let's first check the ones that are inside. So as far as our current value is inside our new array of linked list elements, as far as it is inside, we're not supposed to return the same thing again. So because one is already inside here, at this point, we're going to change the pointer. So we're going to, instead of having 3 is current at this point, instead of having current.next to be 1, we're going to switch it. So current.next will now be current.next.next, basically. Let me see how we can write that in simple English now. So looking through the linked list, we check if the next element is in the visited Okay, if it is, okay, set a new pointer. Let's do like this. Reset the pointer to the next dot next of the current. Does this make sense? Does this make sense? Someone needs to answer me. Let me know that we're on the same page. Okay.
1,000%.
It makes sense, right?
Right.
Okay.
If you can you use word wrap?
Oh yeah, sure.
Yeah, just so that we can read.
All right. So we're looking through the linked list, and we check if the next element is in visited. Now, if the element is in visited, we reset the pointer to the next of our current element. Okay. So now we're going to handle something else now. So if we're going to handle the else part of it now. So the else part of it basically is going to be if our current dot next is not in the visited. So in that case, if our current dot next is not in the visited, we're going to add that value right now. We're going to add the value inside our visited list, and then we're going to change the pointer to current dot next. So let's see. So this is, let me write it as else so I remember. So else, so in this case now, this is check if next is in visited. Else, if not in visited, add the value into our visited list, okay, and change the current graph and change the pointer basically. And since this is a loop, this will continue happening till we've gone through our elements basically. Okay, so this is like a breakdown of what we're going to do. So now that we have all this in place, let's start working. Okay, I don't know how I wrote this without sticking well. All right, so let's start working now. So the first thing says, what's the first thing that we're looking at? Check if the linked list is empty, and then hold on, check if the linked list is empty, and then check if the head is none. If it is, return none. Okay, all right, so let's start working. Okay, so let's do like this. Have if our linked list to head is empty. Linked list to head. How do I write that again? Yes, then we'll return none. Okay, that means nothing can be done. We'll just leave that there. Okay. Now let's move on to the next part of our. So now the next thing is to set the head as our current value, right? Okay. So let's set the head. Current should be equal to linked list dot head. Okay. And this is head. Okay. So now current is equal to linked list dot head. Okay. So the next thing is create a container that holds each unique element from the linked list. So we should use set, right? So let's create our visited. Should hold unique elements from our linked list. So we should use set. Set is going to help us. So we're going to take it in as an array. So we'll take in the first one from there at that point. Okay. So now if current.next is not none, then we're at the end of our linked list, right? All right. So that is where our loop starts. So let's have, well, the next element is not known. There's a jump like that. So while it is not known, so the first thing we're going to do now is look through the linked list, okay? And if we check if the next element is in visited, so we check if the next element is in visited, and then if it is, then we reset the pointer to the next dot next, right? Okay, so let's see, how do we propose we do that? So we'll have while current dot next is equal to none, not none, if current dot next value current dot next dot value is in a visited. If it is in a visited, what did they say we should do? If it's in a visited, return the pointer to the next dot next of the value. Okay. So if it's in a visited, we're going to swap the pointer. So we'll now have current dot next will now be current dot next dot next. So this is us resetting the pointer now. So instead of the current dot next of 3 to be 1, we'll now set the current dot next of 3 to be 4. That's current dot next dot next, basically. So we're doing at that point. Okay. So now else, where is it? Where's that else? Okay, that's it now. So else, let's jump down here and have our else. Else, so what do we see should happen? So we add the value into our visited list, and then we change the pointer, right? Okay, so else what we do is to add the value into our visited list, right? So that'll be visited dot add, then adding a current dot next value. Okay, so when we're done adding, we now change the point. So our current value is now current dot next. Okay, and then we'll return our linked list. So we'll return our linked list. What was our linked list called again? Okay, return our linked list. All right, and that is it. Now, hold on. Let's see what is the problem with this now. Why is it trying that error? Wow, correct, doesn't it? Oh wow. Why is the keyword in small letters? Okay. Alright. Okay, so that is basically it. So now if we want to, let's just look at it again. A real quick rundown of what's going to happen now in this. Using what we have now, let's actually solve the problem and see what will happen. So we have our function remove whatever, remove the link, what do you call it? Remove duplicate from linked list, right? So we have our linked list as 1, 2, 3, 4, and thereabout. So in a case where head is none, return none. In this case, we know what the head is. The head is 1, right? So in the case where we have head, we're setting 1 to be our current value, right? So we set 1 to be our current value at this point in time. Perhaps I should even be writing, let me see if I can be writing it here now. So in this case, we have 1 to be equal to, or the other way around, current value is equal to 1. Okay. So now in this case, we're adding 1 to a set and setting it to this thing, what do you call it? What do you call it now? Adding one to a set.
So
Adding one to, can you hear me?
yeah, it's taking the current node head and converting it to a set.
Oh yeah, that's true. Forgive me. Yeah, so it takes in the current node and converts it to a set by passing it in as an array, basically. And then the next thing now, our while loop. So if the current.next.value is invisited, then everything that we extend basically keeps happening and happening. So now let's just run the test for this. Okay. So in order to run this, I think I wrote the test somewhere. Anyways, let's do this. Hold on, let me fetch my test from where I kept it. I have a test for that. Okay. Hold on. Drop this here. And I think it would print our remove tools LL. Okay. This won't give us what I want. So instead, I will print. Let me see what I would print. Okay, so I'm going to print out the values. So let's use this instead. Okay. So what we're going to get basically, if this works, where is it? Where is it now? Remove those. All right. So if our function works, our max value is supposed to be well 1, 2, 3, 4. So our max value is supposed to be 4, basically. So if our function works, we're going to have 4 printed out there. Hold on. There's an error. Let's see. What's the error? Line 2. That's weird.
I think the terminal is on
Oh, the terminal is still on
Python mode, I think. Yeah.
Okay, I was wondering what the problem must have been. All right, so, and that is it basically. So perhaps to confirm our add here, so I guess the values now should be 5, I guess. Oh wow, something wrong. But I guess we all get the concept behind like using linked list to solve our problem basically. So that's the main idea anyway. All right. Okay, Victor.
Yeah, all right, so we'll be moving on to binary trees and binary set trees. So I was going to share my screen now, so we can get started. All right, so we'll first start off with the binary trees. So what are binary trees? I'm sure we're all aware. Binary trees really are like they're a really efficient data structure for storing nodes really. So and where does binary come from? It comes from the fact that each node has a maximum of 2 children nodes or of 2 child nodes. So we know with a binary set tree, with a binary tree, you have a parent node and a maximum of 2 child nodes, a left child node and a right child node. So then what's now binary set trees? So they're like a more specialized form of binary trees where there's an additional constraint. So for a binary set tree, the left child is always less than the parent, and the right child is always bigger than the parent. So what does this help us do? So if you store your data in that form where the left child is always less than the parent and the right child is always bigger than the parent, then it makes it really, really easy and efficient to search for data. Because imagine you have a binary search tree with 1,000,000 nodes, yeah, and you're looking for a particular node. You know, once you start from the root node, which is the first node, yeah, and the value you're looking for is bigger than the root node, then you know the entire left is out of the equation because it has to be to the right. So it means with like each iteration or with like each operation, you are reducing the size of the binary tree by half, which is like a binary search algorithm, and that's the log algorithm, which is like really, really efficient. So that's what a binary search tree helps us do. It helps us arrange our data in such a format that makes it really easy and efficient to do binary search algorithms. So similarly to what Melke did, there's this site that helps you visualize it. So now let's take an example. If we have a binary search tree with a root node of, let's say, 10. So now this is our binary search tree for now. We have just one root node, no children nodes at all. So if we're inserting 4, for instance, because 4 is less than 10, it goes to the left of 4. Or it goes to the left of 10, I mean. If we're setting 15, 15 is bigger than 10, it goes to the right. Now, if we're setting 2, so remember, comparisons always starts from the root node. Whenever you're adding anything, the comparison starts from 10, which is our root node. So it compares 2 to 10. Since 2 is less than 10, it checks the left child of 10, which is 4 in this case. Since 2 is less than 4, then it goes to the left of 4. So just show that 4, then it goes to the left. Now if you add something even smaller, 1, once again it starts from 10, it goes to 4, it goes to 2, then it goes to 1. Insert. See. So now imagine, okay, let me add a few more things. Let me add 20. Let me add 14. Let me add 12. All right, so we have this as our binary tree. Imagine we are looking for 1. And in this binary tree, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 nodes. If we're using like a linear search or something, the worst case for that is big of n, because we have to check every node and look for 1. Yeah, so with the binary search tree, yeah. So we start from the root node. We're looking for 1. So we compare 1 to 10. Since 1 is less than 10, it means this entire right part is out. This entire right part is out, and then we focus on this left part. So we have 4. We compare 1 to 4. Since 1 is less, we go to the left. We compare 1 to 2. Since 1 is less, we go to the left, and we have 1. So it's like we're cutting off half of our binary search tree with each iteration. So that's really what makes binary search tree useful. So any questions so far? All right. So so I'm going to use this binary search tree to solve a problem now, and let's just get started on that. So it's a lit code problem. So let me just grab the question. All right. So the question says, given a binary search tree, find the lowest common ancestor of 2 given nodes in the binary search tree. So let me show you what that means. So it means if we have 4 and 15, the lowest common ancestor is 10, since that's the closest ancestor. If we have 14, and 20, the lowest common ancestor is 15, since that's the closest ancestor. If we have 2 and 14, the lowest common ancestor of these 2 nodes is 10, since that's the closest thing that like connects to both of them. So that's what it means. So for our problem, we have a binary search tree, and we have 2 particular values. I want to find the lowest common ancestor between those values. All right, so let's get started. I'm just zoom a little bit. All right, so we have def lowest common ancestor. It takes in the binary set tree. It takes in like left or child one, and child two. Right. So how do we find this? How do we find this? Let me pick a different example. All right. Once again, let's assume we want to find the lowest common ancestor for 5 and 9. You know, 5 and 9, they have an ancestor as 6. They also have an ancestor as 4. And they also have an ancestor as 3. But the lowest is 6. So 6 is what we want. So we start from 3. Since the two values that we're looking for, 5 and 9, they are both greater than 3, then we know the ancestor has to be confined to the right path. So we can eliminate here. We can eliminate 3 and 1, and then we can restrict our calculations to from 4, 6, and from 4, 6, 5, and 9. So we compare 5 and 9 to 4 again. Since both 5 and 9 are bigger than 4, then we know it's confined to this right path, and then we focus on this right. So we have 6, 5, 9. And now we have, since 5 is less than 6 and 9 is bigger than 6. So we know that's the middle point, and 6 is the ancestor, and we return that. So I would go by it again. When we have two values, we always start from the roots node, and then we compare the values. Since 5 and 9 are both bigger than 3, we know 5 and 9 have to exist to the right of 3, and we can eliminate everything to the left. Assuming we had, let's assume we had 0 here. Yeah, and a million more items. We can restrict everything we are doing to the right. So we are done with 3, we go down to 4. Since 5 and 9 are bigger than 4, then we can cut off 4, and we restrict ourselves to 6, 5, and 9. But now 5 is less than 6, and 9 is bigger than 6. So we know that's like the middle point, and of course that's an ancestor. So we return 6 as the lowest common ancestor. So another example, we have 3 and 45. We have 3 and 45. We want to find the lowest common ancestor for those two nodes. The root is 80 in this case. Since both, so we have 30 and 45, and root is 80. Since both 30 and 45 are bigger than 80, we can get rid of the right, and we know the lowest common ancestor has to be restricted to this particular range. Now we are on 40. Since 30 is less than 40 and 45 is bigger than 40, we know 40 is the middle point between 30 and 45, and therefore it's an ancestor. So that's kind of the kind of idea I want to go into the problem solving with. So does anyone have any questions about that so far? All right. So let's start off with coding this out. So like we did, so we're going to compare the values of child 1 and child 2 to the value of BSTs. Okay, let me just code up a quick binary search tree class before we start off with this. Just a very small one. So class binary search tree. What's the constructor? Takes in a value and it sets the value to be this value. Yeah. And of course, when we start off, the left, it has no children since this is the only value. So self the left is of course none. Self the left is obviously none. And self the right is also none. Right. So this is our initialization function for our binary search tree. So now let's have, I think we only need an insert function for this. So let's add an insert function. It takes in a value that I want to insert. And then, of course, we compare. So if value is bigger than or equal to self the value. So there are two cases. So when setting a value that is bigger than the value we have currently, So there are two cases. It's either there's no node to the right, or there's something to the right. So we first check if there's no node to the right. So if self the right is none, so if there's nothing to the right, so we just insert self the right, just becomes a new binary set tree with that value. But if there's something to the right, then of course we just call this recursively. Self the right or insert value. That's for the first case if the value is bigger than the value of this binary set tree. Now if it's less than, so else, so we just do the exact same thing. If self the left is none, and self the left equals a new binary set tree with that value. And of course, else if it's not none, just call insert recursively on the left bit. So self the left dot insert value. And that's just a really simple binary set tree that has an insert function. And that should be all we need. So now let's go back to our lowest common ancestor algorithm. So now all we do, remember, is to compare. So we just compare, it takes in the binary set tree, takes in the left child, and takes in the right child. So we need to compare the value of the binary set tree, that's the cell of value, to the child 1 and child 2. So if child 1 is greater than the st the value, and child 2 is greater than the st the value, so it's similar to this case. So 5 and 9, we want to find the lowest common ancestor. Since they are both bigger than the root node, which is 3, it means we restrict ourselves to this right-hand part. All right, so in this case, all we just do here is we just return, so we call this function recursively, we return lowest common ancestor. But now in this case, remember we are restricting ourselves to the right part. So now BST becomes BST the right. Yeah, BST the right. That's for the first case. And for the second case, that's this other case here. So here, if you are finding for 30 and 45, since they are both less than 80, it means we are restricted to this left-hand bit. So if child 1 is less than BST, the value, and child 2 is less than BST, the value. So just really similarly, return the lowest common ancestor. And now, remember, we are cutting off the rest. So what we pass in here will just be BST.left and child 1 and child 2. So now for the base case, of course, every recursive algorithm must have a base case. So if it's neither of these two, then it means we've reached, if it's neither of these two, then it means we've reached, like for instance, in this case, we've reached 40. Since 30 is less than 40 and 45 is bigger than 40. So once we've reached a point where we've reached a number that splits the two children into 2, then we've reached the lowest common ancestor. Yeah, so in that case, just do else, just return BST dot value. So yeah, this is a very simple implementation of finding the lowest common ancestor. Any questions so far? All right, so of course, every recursive algorithm can be implemented iteratively, because if you have a big enough BST, there's a likelihood that you smash your call stack with this, because it keeps adding to the call stack. So now let's try and implement this like with a recursive algorithm. With an iterative algorithm, I mean. So def, I'll just copy over this. Iterative. Now for an iterative algorithm, you'll probably be using a while loop instead of instead of recursion by using a while loop. So in this case, so while BST is not known, yeah, so it's going to be very similar to this. So as long as BST is not known, yeah. So similarly, we just check if child 1 is greater than BST dot value and child 2 is greater than BST dot value. In this case, you know what? Let them just extract node to be equals to BST. So while node is not known, in this case, we just set node to be equals to, since it's greater than, so node becomes BST dot right. Then for the other case, if it's less than, if it's less than, okay, we're checking node here. So checking node here. So node becomes node to left. And so by the time we exit this while loop, then we know for sure that node contains lowest common ancestor. And at this point, we just return node to value. So yeah, that's the exact same algorithm, but this is iterative with the while loop, and this is recursive, calling the function recursively. So now
can you just look at line 38? I think you forgot to switch one of them.
Oh yeah.
Yeah, just yeah, nice.
So so yeah, that's it. So let's test a few examples and let's see if this works. All right, so let's create a new binary set tree. Let's say BST equals to binary set tree, and let's just test for this example that we used here. So the root node here is 80. So we're passing 80 here. And we're inserting 40 and 85. All right, so let's insert BST. You know what? Let me just, for I in, want to insert 85, then want to insert 40, then want to insert 30 and 45. Then want to insert 1. So for I in this, BST do insert I. So we have our BST filled with these values. All right, so let's find the lowest common ancestor. Just print this, print lowest common ancestor if passing our BST. And we are looking for, let's do for 30 and 45. We expect to get 40. So let's see what happens. 30 and 45. Yeah, so we have 40 here. So let's try something else. Let's try for 45 and 1. Does anyone have an idea what that would be? The lowest common ancestor of 1 and 45. No,
I have an
email.
idea. Who else has an idea?
1 and 45, the lowest common ancestor.
I think it's going to be 40.
Sorry?
I think it's going to be 40.
All right, let's see if that works.
I think 40 as well. Yeah.
For 1 and 45. Yeah, so it's also 40. So yeah, that works. Yeah, so I believe we found a good approach to that problem. So any questions about what we've said so far? Or anything you want to clarify about or something you're not clear on? Yeah, because we still have a bit of time, so all right.
Yeah.
So
If there's no questions about these data structures, are there any questions about the build week?
Yeah. All right. I guess
maybe we could see a little bit of Django introduction then.
Yeah, we can go over. There's a bit of code prepared for the build week. You have access to it on the training kit. I recommend you to take a look, and there's quite a bit of explanations going on there. Let me just show you. So here on the training kit, let me just go all the way up. Yeah, so if you go to the CS Unit 1 build and down here, you'll reach this link section where you can take a look at the repo, right? This repo kind of lets you know a lot about the build week. So there's actually some guides here. And there's also, I believe there's also like another, yeah, there's quite a lot of different ones. Have you guys taken a look on what you're supposed to do on the build week?
Nope.
Yeah. Give me a second. I'm trying to find my old project so you can have an idea of what you'll be doing next week. Just.
Yeah, I believe there was an actual like standard base code for it. I can't really find it here. It might be a bit below or something. But yeah, the main gist of the build week is you're gonna create a server for a game where you use Django to handle your server side, and the client side can be whatever you want. You can use Django as well, and or you can use React like you've learned before. The goal is to create a map where you have rooms, a minimum of 100 connected rooms in that map. Each one of them should have some description or a title, yeah, some text related to it. And yeah, they have to be connected so the player can move around the map itself. That's MVP. There's also a stretch part where you would implement chat rooms. So for each room in your map, you would have a chat where only players on that room could chat amongst each other. So that's basically build week.
So is this like not a copy, but similar to the one we did, the text-based game or whatever we did?
Yeah, you've already worked with this before on one of the afternoon projects. The player was moving around in rooms. At the time, you just have 5 rooms and a few commands to deal with. Now it's a bit larger, right? You actually have to have a minimum of 100 connected rooms, and each one of them has to have texts attached to it. So obviously you can do it by hand, but I don't recommend you do it by hand. I recommend looking into generation of, yeah, just a map or also generation of text. Yeah. Any other questions?
All right.
Yeah.
I have mine loaded up, so if anyone is interested, I can quickly show you a demo of how it should look like. Sorry. Yes. Just move this over.
Can we use our previous code? Like, it's probably the Django, so we are not actually using it, but can we base ourselves on it or something?
Yeah, you can use your own code, of course. So if you have already some logic built up with that of course helps. The main goal of the build week will be the map generation and just getting the player moving there. Yeah.
All right, so you're going to have like a login and register page. So let me just understand.
Yeah.
This is also Django backend.
I'm gonna show my own as well, just because.
Yeah. So yeah. So you have a map and you have a player, and it's like a maze because you have, this is like the end goal. We have a treasure. We have like a treasure here at the lower left bit. So the goal is like to move your player and to get here. So, and of course, when you're generating your map, there has to be a path because you can't just have a map that stops somewhere and blocks off movement. So you have to be able to have a continuous path that leads from the input to the exit. So I hope I can remember my spinning well. All right, yeah. So you get here. So yeah, that's kind of it. That's really it.
I have a question for you. You don't really have rooms, or you treat like each position as a room?
Yeah. It's like up to your interpretation. You should just have 100 connected things. So for what we did, so each of these things are like rooms, and then you have a part connecting rooms. So each of like these tiles are rooms, and then you have a part connecting rooms.
If I'm correct, like even the walls are rooms, right?
Well, in our case, we had the walls as like barriers, not really rooms in that sense.
Okay, yeah, okay.
So yeah, but this is just an example. You can do it any way you want, just to have general concepts. Like you should have at least 100 connected things that you can move between. It doesn't have to be rooms. It doesn't have to be, I mean, yeah, it should be rooms, but it doesn't have to be like physical rooms, just anything. So Melky, can you show yours also?
Yeah. Let's see. So mine doesn't have that much graphics, but yeah, it's very similar. So there's a login, just continue, start and exit menu, and then yeah, just starts, right? And yeah, in my case, my map is like each room is a white square, and the one you're on is the red, of course. Yeah, if you try to move, you can use the keyboard, right? And yeah, it just does it like that. So even these rooms where it seems there's a gap, it's just a long corridor. Yeah. So also my text and titles are all generated for all of these rooms. So basically, there's a script in the backend that generates all of this. I just tell it the number of rooms. And yeah, obviously, I just have 100 here because 500 will be a much bigger square. But yeah, also, I have the chat here. So basically, if I'm in a specific room, it tells other people that I've entered it, and it lets me know that there's someone else in here in this room. So yeah, if there were other players in here, we could chat, and yeah, that's basically it.
I have a question. Is that your room layout? Is it a matrix, like, and you just generate rooms all over? Or do you actually link them? Like, you generate one and you go and link all of them? Because Just jump from one place to another, and you said it was a corridor, but I would not assume that. I would do it like actual links, and you could only go through a path if there was a path, not like jump.
Yeah. So in this case, what I did was it generates the map randomly. So each row that you see here, each row of squares, it randomly assigns 0 or 1 if it's a room or not, and then it just keeps going from 0 to 100, right? Then these other ones, right? For example, I'm on 72. What it does is when it tries to find connections, it goes forward and sees a room, goes backwards, sees a room, goes down, sees a room, and connects, right? And then goes upward and sees a room there, right? So it connects to 44. Okay, so all of my rooms are connected to all sides if there's a room there. Okay, so that's why they're corridors. Okay, so but yeah, you could also apply another factor of randomness where a room would not connect after there's like 2 empty squares or something like that. You could also do random like that. Yeah, that's
So you are saying they are actually linked, not just points on a matrix?
they are actually linked. So there's an actual class room, right? Like you have on the afternoon projects, and you have north, south, east, west. And yeah, each direction has the link, and that's why it works. Otherwise, if I clicked here to go up, my request to the backend would not allow me to go up because yeah, it's checking if there's a room to the north of this room, and it only goes up after I get the response. I can actually try and show it. If I, yeah, there's also console logs. Yeah, okay. So yeah, if I go down, there's a move request, right? Telling it I'm on room 66 and I want to go north. So north to 47, see here. So is that, was that what you're looking for?
Yeah, cool. Because I was thinking you might have cheated and like just do a matrix. Link
Yeah,
them.
there's ways to go around it for sure. But yeah, it is connected. So yeah,
So Melky, how many rooms you said you have?
100.
100. So do you have a different title and script for every room?
Yeah, each room has a different text and title. They might have very similar words because at some point I got tired of writing words.
Okay, manually. I see.
Yeah,
So,
yeah. Well, you don't have to, because I mean, you can just have like phrases, like short phrases, and then just randomize it and just come up with 100.
yeah.
I was just curious if you actually wrote the description for 100 different rooms. Like,
No. I wrote a bunch of arrays with words where if you join them in the correct order, they make sentences that make sense. So, and then I have like a randomizer. So each array has a topic. For example, array 1 would be just A minor, right? If I have this, and then if I change rooms, like it has A narrow. So it has array 1 would have like a bunch of adjectives. So A large, right?
yeah, I see that.
A modest, right? So yeah, it has a bunch of things, and then there's like a second array with a bunch of the second part of the word of the sentence, right? There's a bunch of arrays, and then they're all random, all randomized for each room.
Cool.
You know, you can have less words also. So don't start thinking of
Oh yeah, it
100.
doesn't have to be like
Yeah,
a
because in our
full.
case we had just 10 stories basically all through. But we had 100 rooms, so we had just 10 stories. Yeah.
Yeah, basically a paragraph like this should be cool. Yeah, you don't have to do like a full story for each room. Yeah.
All right. Also, if you're not super confident about writing your own algorithm for the room generation, or for the maze generation, if you have 100 rooms and you're not sure how to connect it, there are a few popular algorithms. There's the binary search algorithm for maze generation. So you can just look up those and try to understand how they are done, because they've been tried and they've been tested, and you are sure that you'd have like a path between the beginning and the end, because that's the important thing. You have to be able to move across your entire maze. So you can just look up popular maze generation algorithms and try to understand it and implement it. All right. Yeah, so any more questions before we close up for today? Yeah.
What's for dinner?
I've not had dinner yet, so I have no idea. All right, so good luck in
Just one more thing. I recommend starting researching how to deploy Django on your Roku by at least Wednesday, maybe before. So try to get your project running live, because if you get problems deploying, it doesn't exist. Yeah, it's a problem. So
You could do Gabe's method of having the smallest code running, even if it's your hello world or welcome to Django or something. Just have that running and then try deploying. That would help.
Exactly.
Yeah, because it's not very easy to deploy a Django project compared to Node, because it's not like it's just a few steps. You have to install some libraries and do some configuration. So it's better you do it early, so you have less code to deploy and it's easier to debug. And if you have like a whole lot of code and then you have no idea where to start from. And we are going to share some resources once this call is finished to help you and to give you some guidance. But yeah, thank you guys for joining us today. And yeah, okay.
Yeah, and yeah, of course we'll be there in the build week. So yeah, ask questions.
Bye guys. See you tomorrow.